Okay, so the first thing I want to do before I get to the no cloning theorem is talk about tensor products. So suppose we have 2 qubits. What is the state space? Well, let's think, what is a basis for the state space? How many distinguishable states can you find? Anybody? Can somebody give me, yeah?
0, 0, 0, 1, 1, 0, 1, 1.
Yeah, 0, 0, 0, 1, 1, 0, and 1, 1. So how can you distinguish them? Well, if you wanted to distinguish these two, you could measure the second bit. If you wanted to distinguish these two, you could measure the first bit. And in fact, there are 4 distinguishable states, which means that if you have 2 qubits, your state space has dimension 4. And n qubits, can someone tell me what the size of the state space for n qubits is? 2 to the n. And I probably don't need to write down all the basis states. And I should say something that this is one way of expressing this state space. We can also write it as 0, 0, where this applies to the first qubit and this applies to the second, or 0 tensor 0. So this is 1. And if we name our systems A, B, we can make it clear which qubit belongs to which system by putting, say, AB here, or AB, or AB. Okay, so that's the no cloning theorem. That's the tensor products. And let's do a little bit more tensor products before we get to the no cloning theorem. So yeah. Well, how many degrees of freedom for a single qubit? Well, there were 3, remember, because you had a block sphere, and the qubit could be anywhere on the block sphere. So how many degrees of freedom for 2 qubits? Well, and when we have alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1. So that's 2, 4, 6, 8. But then we have to subtract some things. But sum alpha I squared is equal to 1. So that gives you 1 fewer degree of freedom. And wait, 3? no, this is 2. I mean, it's on the surface of the Bloch sphere, so it's just 2 degrees of freedom. So, I mean, yeah. And 2 qubits. And we also have a global phase, which is irrelevant. So that's 6. And n, well, we really have 2 to the n minus 2, because, again, we have the sum of the squares is 1 and a global phase. So what does this say? Well, this says that there are 4 degrees of freedom if we take the product of 2 qubits, each of which is in its own state, and there are 6 degrees of freedom if we look at the general state space of 2 qubits. So that means there are some states of 2 qubits which cannot be factored into 2, into 2 things. So a separable state each qubit is in a definite state and alpha 0 plus beta 1, let's call this qubit A, times gamma 0 plus delta 1, let's call this qubit B, is equal to alpha gamma 0 0 plus alpha delta 0 1 plus beta gamma 1 0 plus beta delta 1 1. So this is a qubit in a separable state where you can say these 2 states each exist. So otherwise, the qubit is an entangled state e.g. 1 over root 2, 0, 1, minus 1, 0. And here, you cannot separate this state into one state of the first qubit and one state of the second qubit.